Welcome everyone. My name is Heiner Litz. I'm going to present CRISP, Critical Slice Prefetching. This work has been done in collaboration with Grant and Partha from Google. So the problem that we're addressing in this work is to reduce processor stalls induced by cache misses and the resulting long latency DRAM accesses. So this is still a significant problem of modern microprocessors. For instance, Google has reported that in their fleet, processors spend roughly 43% of their cycles waiting for data to return from main memory. This causes low performance, low instructions per cycle, IPC, and despite the decades of research on caching and prefetching, this problem hasn't been solved satisfactorily. And the reason for that is that existing hardware prefetchers are either infeasible to implement due to hardware cost and complexity, or they are unable to address irregular memory access patterns. So let me motivate our work with some example. Over here, you see a two-nested loop, whereas in the outer loop, we perform an irregular memory access pattern, such as a pointer dereference or linked list traversal. And this memory access is irregular. It's hard to impossible to prefetch by existing hardware prefetchers, and it causes low IPC. On the other hand, in that kernel, we see an inner loop that performs an embarrassingly parallel computation operation. And this one will be executed with high IPC. So we measured the performance of this code on a modern out-of-order execution machine. And what you can see here in the yellow curve is that we are alternating between two phases, one with low IPC, where we are handling that irregular memory access pattern, and a phase with high IPC shown at the top over here, where we are executing code with high IPC. This results in a non-optimal average performance shown as the yellow dashed line. What we're going to propose and show in this work is CRISP, which enables a much higher average performance by ensuring that the processor most of its time operates at high IPC. And the key insight here is that we are going to move the irregular memory access before the high IPC kernel of the code over here, so that we can execute the long latency load with the compute intensive code portion at the same time, hiding the memory access latency. I want to provide some more details on why modern and existing out-of-order execution units are unable to already address this issue. So modern out-of-order machines utilize branch prediction and speculation to unroll loops in hardware. So on the right, we can see two iterations of the outer loop, showing both the compute-intensive kernel as well as the irregular memory access. And so although via branch prediction, processors can look ahead and see those future instructions, such as the irregular memory access, they are unable to execute it early. And the reason, therefore, is that first, they don't know that this load down here is particularly critical. And second, they implement scheduling policies such as oldest instruction first, which make sure that while we're having sufficient ready high IPC instructions available in our reservation station, those will be issued first before the critical and long latency load will be issued down the CPU pipeline. So if we want to address this issue, we need to come up with a mechanism that guarantees that this linked list traversal or irregular memory access is executed before the compute-intensive kernel. So this is the CRISP technique that we are proposing. In the first step, we will determine long latency instructions. Most often these are loads, but we can handle other instructions such as division as well. And we'll also later show that our technique can be applied to hard to predict branches as well. These long latency instructions are purely determined in software via PMU counters. We then extract critical instruction slices of these long latency instructions because prioritizing a load is not sufficient. We also need to prioritize the instructions feeding into that load, such as the address generating instructions. This step is also performed in software by analyzing instruction traces. And third, we then tag these critical instructions as prioritized and will enable the CPU scheduler to issue them before other instructions in the schedule. This part of the technique is implemented in hardware. Let's provide some more details on these three steps. So first, we need to determine the critical instructions, those that we want to prioritize by the scheduler. This requires to monitor all the loads that a program exhibits to count its execution frequency and miss rates. And because that would introduce a lot of hardware complexity and metadata storage, we leverage already existing PMU hardware performance monitoring unit counters of CPUs, such as those from Intel, ARM, and AMD. These mechanisms not only allow us to extract the PCs of those instructions, but also the stall cycles they incur and their latency. We then extract the load slices by capturing entire instruction sequences and then backwards traverse the register operands of these instructions to extract the address generating instructions of a long latency load. And we then prioritize all instructions in the slice by recompiling our original binary and prepending a so-called priority prefix to each critical instruction. So here's some more information about how we extract these slices. On the right, I show a code snippet that represents the same kernel that we've seen before. Via PMU counter, we determine that this source code line induces the memory access that suffers from high LLC cache miss rates. This is a move instruction in that case of address 15 ED. And then we analyze the source and destination operands of this and the further instruction to traverse backwards through our trace, extracting the entire slice in the process. So we perform this in software as well, because by operating on instruction traces, we have the whole sequence in front of us, and we can easily traverse these instruction sequences in forwards and backwards directions. We then optimize a number of optimization mechanisms to prune non-critical instructions from the slice and to drop large slices entirely until we have a good set of critical slices for a given application. Lastly, we recompile this application by tagging each one with a new instruction prefix, which ISAs such as x86 support. We just define a new prefix that we can append to every instruction that should be regarded as critical. We then extend the H-matrix-based RAN scheduler implemented in most modern microprocessors by observing a vector, so-called priority vector, that tags every instruction that is waiting in the reservation station in the processor as being critical or not. So as you can see on the right side figure, for each instruction in the reservation station, we maintain information about its readiness, whether its source operands are available, about the age, meaning when has this instruction been dispatched into the reservation station, as well as its priority. We combine these informations to implement a ready, first prioritized, then oldest instruction policy, which ensures that high priority instructions are issued into the pipeline first. And if there are no longer any prioritized instructions in the reservation station, we will issue according to the age of the instructions. Some more comments about why pure hardware and software techniques are insufficient. The hardware complexity as well as metadata state required to implement CRISP as a pure hardware architecture is challenging. First of all, we need to maintain significant amount of state to determine critical loads. We need to maintain large tables that capture load PCs, their miss rate, and execution frequency. Secondly, we would have to implement a mechanism in hardware to extract instruction dependencies and to implement the backwards data flow analysis. Both of these tasks require and introduce a lot of hardware complexity and storage. Secondly, a pure hardware implementation only delivers suboptimal load slices because it is impossible in hardware to also observe dependencies through memory and not only through registers. As a result, these load slices are often incomplete and we cannot ensure the same performance improvements as with the CRISP technique. And this is particularly relevant for x86, which performs a lot of register spilling. Secondly, we also cannot easily implement these optimization mechanisms to prune instructions from those slices, which we can easily do in software. Pure software techniques are also infeasible, as while we can utilize compilers to host loads and reorder them within the program sequence so that their latency is partially hidden, compilers are very limited in the opportunities they can leverage here. And the reason is that they need to be pessimistic without reordering loads across basic blocks or loop iterations. So to do so, you really need hardware speculation mechanisms such as branch prediction and the option to flush misspeculated instructions. And as a result, hardware techniques are needed to get the full benefit of instruction reordering. We implemented CRISP as a co-designed hardware software approach. So in software, again, we extract the critical instruction and their slices. We then tag the binary as critical. And then we modified a microarchitectural simulator, in particular the scheduler, to observe this criticality instruction prefix while scheduling instructions. And what we found is that CRISP performs an IPC uplift of 8.6% over the out-of-order baseline we compare against. In our work, we also compare against 4 other baselines referred to as IBDA, Iterative Backwards Dependency Analysis, These are hardware-only techniques that suffer from several of the shortcomings I mentioned. And as you can see, the gains that are achieved by IBDA are much smaller, while IBDA introduces much higher hardware complexity than CRISP. I want to talk about one more thing, that is CRISP can also be leveraged to accelerate branches that suffer from high misprediction penalty. So what we're doing here is, again, via p-mu counters, we determine branches that frequently mispredict and those that are hard to predict. We also extract the slices of the instructions computing the branch outcome, and then we prioritize those slices. As a result, these branches do not become easier to predict. However, we can resolve them faster, and as a result, we reduce the misprediction penalty induced by those hard to predict branches. This alone provides an 18% uplift, for instance, for LBM, as shown here by the blue bar. And when combined with critical load slices, this even improves performance by over 30% over the out of order baseline. This is everything I have. Thanks for your attention, and I'm happy to answer your questions.